To the module Introduction to Machine Learning. We will explore the fundamental concepts that form the foundation of modern machine learning system. We'll also demystify what machine learning is, how it differs from traditional programming, and identify the key components of effective ML solutions. This foundation will prepare you for the generative AI concepts as well in our upcoming sessions. I am Navi Kaur. I've got 17 years experience in IT, 5 years as an AWS technical trainer. I began my cloud journey in 2018, but my machine learning journey only began in 2024. I have been deeply immersed in the AWS ecosystem ever since. I'm passionate about sharing knowledge and dedicating to our other learners as well for their upskilling. Okay, our agenda is to learn artificial intelligence fundamentals, machine learning use cases, and various ML types today. Then we look at the ML development lifecycle. We'll also examine AWS's suite of managed AI ML services with a special focus on Amazon SageMaker AI. What is artificial intelligence? Around 70 years ago, humans envisioned that computers could shoulder their workloads, which led to the development of early artificial intelligence concepts and research. AI is a field of computer science that enables machines to learn, reason, perform tasks that typically require human intelligence. It started with programmers setting up rules. If this customer purchased shoes, they might be interested in socks as well because there's an established relationship between these two products. So let's show them that. So this can occasionally prompt customers to buy different products from the site, but it means setting up those rules. And when new products come in, to add more rules, that means as more rules are added, the process is taking longer to return a result, meaning customers are waiting for those recommendations to load and likely getting frustrated moving on to another page. And this approach is also cumbersome and prone to human biases, errors, so not good for the long term. That's when came machine learning, where computers were told how to learn from the patterns from historical data to make predictions without explicitly programmed. Let's learn this with a common example, detecting fraudulent banking transactions. So here we have data scientists who have done PhDs, ML engineers. They are looking at creating a fraud detection system. So they start with collecting a large data set of historical banking transactions and then labeling them as fraud or not fraud. So a lot of work here. And then using this labeled data to train a model using algorithms, which are a set of rules that'll then create a model. They will evaluate the performance of this model through testing and training. And once the model is ready, it has learned patterns and characteristics from the input data to distinguish between fraud and legitimate transactions. We will show it a new transaction, and model can predict if it is fraud, and we can then ask it to take some actions as well, like generate an alert or send a notification using our simple notification service to the customer as well. So predictions can be used to take business actions. Now, it is important to note here that building an effective fraud detection system requires close collaboration between all these people working for the bank, between domain experts, and it is a lot of work. Initially, that's how it started. Let's see how we've made it simplified using our tools. So what is a model again? A model is not created manually by programmers, not by similar to setting up rules like in classical programming. So if you just imagine training a young student by showing the student countless examples rather than listing rigid rules, the student will learn looking at those examples. Machine learning also derives rules from the data itself. Predictions made by the model can be used to take business actions, which is why machine learning is of high interest to all areas in all organizations. It's really popular. These models, they rely heavily on the completeness of the input data to perform any useful results. We need to make sure we are giving it quality data set. Model training is done so that it can make high quality estimations or predictions. For example, data scientists could train a medical application to diagnose cancer from X-ray images by storing millions of scan images and the corresponding diagnosis. And what I have done, here's my data set of 1,000 labeled images of cats and 1,000 labeled images of dogs. And along with the images, I have given their respective features such as fur, whiskers, other relevant information to teach my model to recognize images of dog. I didn't give any specific instructions. So over time, the algorithm improves, can recognize dogs in new images it hasn't seen before. It learns the difference. It actually builds an internal understanding, just like our brains do, understanding of what defines a cat or dog. When my model is ready, I give it an image. The model can analyze it, predict it, whether the subject in the image is a cat or dog. So some of the key concepts you need to be aware of in the machine learning modeling are features. Features are different pieces of information about each data sample. So if we are talking about house price prediction, this task will need some data with like things like size of the house, number of bedrooms, locations, maybe color of the house to predict a good price or the right price. Then we have weights. The weights represent how important each of these feature is for making a prediction. When the machine learning is going on, it adjusts these weights during training, try to minimize the errors. So while the machine learning was going on for this house price prediction model, it realized that color is not contributing to the price prediction. So let's give it a low weight. The more important a feature is, the higher its weight will be. Then we have labels. These are the actual true values that the model is trying to predict. For house prices, the label would be the actual sale of the price. The model will look at the historical data. What was the price of the house with 3 bedrooms? There was 5 bathrooms, front yard, backyard. So looking at historical data, if it was sold for $200,000, it knows what are the important features. So the model comprises its predictions of these true labels in the historical data during the training process. Let's look at a data set. We have 2 key components here. We are trying to predict if customers are going to buy ice cream or not. So features are the data that help you make predictions. We have weather and like sweet food. The first feature is whether the weather is hot or not. So an important category in this case. And we also have labels from the past, from historical data. They represent the outcomes of past customers who have or who have not bought ice cream. We trust these labels because they're observed and are unambiguous. Simply put, label is the thing you are trying to predict. So 2 features and a label, very simple example. Features are identified as important in determining accurate outcomes, unique characteristics of the data set. Okay, these are the ones which are going to help us identify patterns and predict future answers. We can measure it, how hot the weather is, it is cold, it's raining. High quality features result in better models. Our feature, how much the person likes sweet, depends on if they are going to buy the ice cream or not. Weights indicate how important the feature is, how much this one feature is going to affect the accuracy. Machines learns and adjusts weights from looking at historical example during the training stage. So here we have our feature, weather, it's important. School holidays is worth 0.6, and like sweet food. We will take it as a feature as well. We saw that earlier, and let's make this one 0.2 and 0.4 as well, like sweet food. So machine is going to adjust these weights. The key idea in machine learning is concept of the context, which is represented by the weights. So machine realized after doing the training, we have this formula which can predict whether a person will buy ice cream or not. So we have customer A, where they realize the weather is very hot and sunny that day, 0.8, but their likeness for the sweet was low, 0.3, not that into sweets. And the machine predicted there is a chance of 50% that they're going to buy ice cream. Customer B, on the other hand, even though the weather was cold and rainy, it wasn't really weather for the ice cream, but their love for sweetness or likeness for sweet things, sweet tooth was great. So based on the feature weights, we can predict that customer B is more likely to buy ice cream even though the weather is bad because of their strong liking of sweet food. That's an important factor. Real life can be complicated. We might want to consider other factors that will affect sale of ice cream, but this is just a simple example to show how machine learning works. Now, machine learning depends on a lot of data from the data sets. The primary data set, which is used to train machine learning, should be representative of the real world scenarios. But data can come in various shapes and forms. We can have labeled data, like a data set of emails with labels indicating this is a spam email and this is not spam. So labels on the email, or we can have unlabeled data, which doesn't have annotations. It could be collection of customer reviews without any categorizations or sentiment tags. We can also have structured data, which is organized like spreadsheet or time series data, which, for example, daily stock prices of company over the past year. Unstructured data that lacks any predefined structure, collection of X-ray images used for medical diagnosis, or social media posts, text, images, videos, a mix. Now, various machine learning use cases you might have already noticed, they're all around you when you're watching television, you're buying things on a retail website. So starting with personalization, ML can be leveraged to customize experiences, products for individual users based on their preferences and behaviors. Machine learning models can be trained to classify, detect, recognize objects, celebrities, people, text, activities in images and videos. And this has application in areas like security, self-driving cars, medical imaging, social media. Applying ML techniques to historical sales data to forecast future demand, optimize our inventory, production, pricing. Using ML to personalize content, make tailored recommendations about the products on e-commerce sites, widely used streaming media, new show suggestions, or scheduling maintenance proactively in the industry, in the factories, before the machine breakdown occurs. Now, why will someone do that? To avoid unplanned downtime and emergency repairs. This is used across industries like manufacturing, transportation, utilities, and it all helps in making them more reliable, operational, efficient. And there are many more examples like Alexa, Siri, respond to commands, set alarms, play music, change lighting, advertisements, chatbot, virtual assistants that can answer questions about coding, robotics platform that teach programming, personal assistants that help you stay organized. So various machine learning use cases are already present. But it's valuable to understand the limitations and appropriate applications of machine learning as well. So we know that machine learning models are trained on historical data. They might not adapt well to rapidly changing environments or new situations that differ significantly from the training data. Or for applications where mistakes could have severe consequences, such as aviation or medical diagnosis of rare diseases, the risk of machine learning failures may outweigh the benefit. It can be computationally expensive, intensive as well, may not be able to make predictions quickly enough for applications that require real-time decision making. Or in highly regulated industries like finance and healthcare, there may be a need for interpretable models that can clearly explain the reasoning behind the decision. So some of those use cases might be machine learning is not a good idea. Or rule-based systems are better, or they require another layer of human decision making on top of that. Because for decisions that have significant ethical implications, such as criminal sentencing or child welfare, witness protection program, we don't just want to depend on the machines to take a decision. There may be concerns about the fairness, accountability of machine learning models. So in these cases, human decision making with appropriate oversight and safeguards may be preferred. Now, machines only make predictions. If you require 100% accuracy all the time, maybe a different kind of solution is better. Data sets. If we only have a small data set and our model then might not be able to find any patterns in that data set. For example, for that ice cream thing, if we only have information from December and January, when the weather changes, season changes, we wouldn't know what our customer going to do in June. So we actually need a lot of data for the machine to make these predictions accurately. Different approaches and techniques are used in machine learning to solve various problems. Let's now look at broad classes or types of these approaches. We have supervised learning, where algorithms, they require training on example data that has been labeled, like that fraud detection model. The transaction, is it fraud or not fraud, from historical data. Unsupervised learning, where the model must discover patterns and structure within its data on its own, create its own labels and classifications for the data. Then we also have reinforcement learning, where the model interacts with its environment and learns to take actions, like in self-driving cars. The machine learning algorithm one will choose will heavily depend on what kind of problem is at hand, because each of these are designed with certain problems in mind. Depending on the nature of the problem, the choice of one of these categories will be made. Let's look more closely into these. In a supervised learning setting, the objective is to develop a function that takes a labeled data set, like this one here, and when generates an output value on unseen data. So we have classification here. We can use classification to predict a discrete class label, means we can figure out what this thing is. Classifying emails as spam or not spam, classifying transactions as fraud or not fraud, classifying if it is a cat or a dog. Because we provided label data, it's much easier for the model to predict. Then we also have regression as supervised learning, where we're trying to predict a number like that house price or a stock price, what is going to be the stock price in a few months, or insurance premium. Many use cases of this as well. So predicting a continuous numerical output variable. The computer is trying to use what it has learned to make a good guess about the price. And a number that can be anything within a range, not just a simple yes or no, like this classification problem here. So output variable in classification is categorical, and in regression, it is numerical. In unsupervised learning, as I said earlier, aim is to uncover underlying patterns and structures and relationship within the data without explicit guidance. This can lead to valuable insights, better understanding of the data. Here we will take a customer segmentation problem and using clustering. An e-commerce website wants to tailor their marketing efforts. They want to analyze customer purchasing habits, browsing behavior, demographic information, and their preferences. So they apply this clustering algorithm to group their customers into various groups here. We have frequent shoppers. They are at the shops all the time. And we have bargain hunter. Only if there's a discount, they'll come. And now it has also grouped occasional visitors. Maybe once a month they go and buy something. So the company can now apply various discounts. For frequent shoppers, they'll give 20%. For bargain hunters, they say 70% off because they know they are going to come only if there's a bargain. Occasional visitors, maybe 5% discount. They're not even going to come even if we give them a bigger discount. That's what the company thought. So these are all for business predictions. Then we have anomaly detection. Basically, finding something that's unusual, doesn't fit the usual pattern or stand out. So the algorithm here will first look at all these apples in this basket and notice that the majority of them have a similar appearance. They're shiny, firm, without any visual defects. It'll describe or consider them as normal, good apples. But if it notices an apple which has discoloring or visual bruises, it can categorize it as anomaly, bad apple that stand out from the rest. So anomaly detection can be used to troubleshoot web traffic coming to our website, examining server logs when regular patterns are being noticed, good, but then if there's suddenly unusual traffic coming, significant surge in traffic coming from a various country maybe, then it can detect that anomaly. Or we can detect anomalies in heart rate to monitor the heart rate of the patients, watching the heart monitor readings when the normal steady heartbeat suddenly shows strange behavior like skipped beats or extra beats, we can then raise an alert. So used in many use cases here. The dog learns through trial and error interaction with its environment. It can receive positive rewards for safe, efficient interaction, negative penalties for not listening, no petting for an hour. Similarly, reinforcement learning is where the algorithm is trained by interaction with the environment. An agent continuously learns through trial and error. Imagine you want to train a self-driving car to navigate through a busy city. In this case, the car would be the agent. So the goal of the car is to go from point A to point B, avoiding obstacles, not going on the grass, and obeying the traffic rules, reaching the destination as efficiently as possible. So the learning in reinforcement learning comes from the agent changing its policy, updating its value function as a result of its experiences in the environment. This is a very good case where we are using robots or self-driving cars or games. Game playing algorithms use it as well. And if you want to learn more about reinforcement learning, because it is a surprisingly different technology from normal things, you can go to this MLU Explain website, and it talks about reinforcement learning with examples, and you can learn some more from here. Okay. Let's now look at the machine learning development lifecycle, which is a structured framework for creating, deploying, maintaining machine learning systems. First, we check if a business problem should be addressed by machine learning or not. If not, we should take a different approach. So what do you think? If there is a small shop owner who wants to ensure she orders the right amount of office supplies each month to avoid waste, should it be resolved by keeping a simple spreadsheet or by creating a machine learning model? Maybe we don't need the model in this case, but what about detecting fraud in banking industry? where is it suited for machine learning? Because it has complex, evolving nature, massive volumes of data involved, especially these days. So yes, for fraud detection, what we'll do is do a problem formulation where we are going to convert the business problem into a machine learning problem, defining it using ML terms. What are we going to achieve by creating a model for fraud detection? Identifying best algorithm for fraud detection. Supervised, classification, great. What do we need next? We need data. We have to collect, ingest the data from various sources, gathering the raw data. This could be from websites, old logs, old transactions, databases, API, and any other digital repositories where we can get the data for our transactions, banking transactions. Once we have the raw data, we want to explore and understand it. We are not going to create the model straight away. We will first look at things like data distribution. Where are we collecting the data from? Is it balanced data or not? The data, identifying any patterns or anomalies, understanding how different features in the data might be related to each other. So we need some tools to do this pre-processing and visualization before we start the training. After exploring the data, we can clean it, prepare it for the machine learning training, because we want to make sure there are no missing values in that data set. Or are there any duplicate values? Maybe we need to remove them. Are there any outliers? Once we are happy with the data prepared, we can start the training. Selecting the most suitable ML algorithm, feeding the data into model, adjusting the model's parameters to improve its performance. So during the model training, the goal is to find parameter values that minimize the difference between predicted and actual value. For example, house price prediction model predicted the house is going to be sold for 100,000. But in the past historical data set, we found the actual value was 50,000. That's a big loss or error. We want to keep doing the training. After training the model, or while we're training the model, we want to evaluate the accuracy as well. Is it performing really well or not? Should we keep on training it? So again, the goal is to determine if the model might need additional data, or does it need any feature engineering, change in how the features are selected in the data set. So we can keep some test data on the side to do this model evaluation. And if the evaluation is not really great, it is actually showing a lot of errors, we can tune the model. We can change a few things while it's doing the training. So model tuning is settings you can adjust to improve the model's performance. In model tuning, we have a very popular word called hyperparameter tuning. It's like when you want to go somewhere, you sit in the car, you adjust your car settings, your windows out, and your seat in the proper position, rear view, mirrors are correct, and all those things. So after the model is ready, we will deploy it. It's performing well in the testing, so now we can deploy it in the production environment where it can be used to make predictions. Do we have another step? Yes, we do. You still want to monitor its performance to make sure it's still working as expected. And we might want to keep tracking the model's accuracy, the number of errors it's making, or change in any data that it's receiving, that unseen data it receives and make predictions on. Has something changed with that? So in this introductory course, you just need to know about what are the stages in the development life cycle. You don't need to go too deep dive into how everything is done, because Long time ago, this was all manual process, but we have now tools which can be used to do all these things easily. Introducing Amazon SageMaker AI, a fully managed service that provides tools to do the data prep, training of the model, building of the model, and even deploying on the model. And then also monitoring of the model. We want to monitor it in production. So we have tools for data preparation, processing, making it easier to handle large data sets for machine learning projects. We can quickly build with one clicks. We can build models as well, test them, use pre-built algorithms, and automate the training tools as well. We deploy and monitor. SageMaker AI also integrate with other AWS services. So usually we keep our long historical data sets in simple storage service called S3. It's integrated with that. We use Glue sometimes for data pre-processing. It's integrated with that. We use Athena to do some simple SQL queries. It's integrated with that. So if you are already using AWS, you will see SageMaker AI fits into all those existing AWS services. Let's look at some of its features here. SageMaker Studio. It's providing developers a faster, more reliable user interface. Now, these developers, they want to run scripts. They are using integrated development environment. So they are running scripts. Why are they running these scripts? To deploy machine learning model, to create and train or clean the data set. But if you are in business, SageMaker Canvas is a no-code, low-code visual interface, a machine learning service that empowers business users to build, train, deploy machine learning models. And they don't need prior machine learning expertise. So people like me and you. Then we have Data Wrangler, providing a powerful way to prepare your data for machine learning, saving time, effort, simplifying the process of data preparation and feature engineering. So let's have a look at SageMaker Data Wrangler. Visual interface. You can import data, can prepare it, transform things, visualize it. You want to see how it looks like on a line chart, or you want to see how it looks like on a bar chart. Is there an outlier somewhere there? Analyze it, all from Data Wrangler. Why? Because data is messy. Data is considered messy. It can have many problems like missing information, incorrect values, inconsistent formats, duplicate, spelling errors, mixed up columns, a lot of problems. SageMaker Data Wrangler empowers users to efficiently explore, manipulate this data, transform it the way they want it. So that will help them with the development of accurate, effective machine learning models. One of the key features of SageMaker Data Wrangler is the ability to transform the data. Each transformation that you apply adds a step to the data flow, creating a visual representation. And there are built-in transformations. First, you want to visualize it. You want to see correlation metrics, which is a table that shows the relations or correlation coefficients between multiple variables, features of the data set. So this helps the scientist or us to understand how different features are related to each other. Histograms are for numerical data distribution. You can visualize using bar charts, scatter plots, time series plots. So very helpful tool, making it easier to prepare our data for model training. Earlier, scientists were spending 80% of the time doing all these things, which are now possible through this tool called Data Wrangler. To train a supervised machine learning model, you need a large high quality labeled data set. SageMaker Ground Truth helps you build high quality training data sets. So what it does, it helps you add humans in the workflow for you. They can help us with the labeling, data generation, model review, and evaluation as well. So let me show you Amazon SageMaker. As I said, Amazon SageMaker AI is to help build, train, deploy machine learning models and scale. It has many features. So we talked about Studio, which is for developers to run the script. Think it in that way because it's like a development environment. We also have Canvas, which is no code, low code for business users. Generate models with one click in Canvas. Look at your data in Canvas as well. And there are many more features. But the one we were talking about is the ground truth, SageMaker ground truth, where we can ask humans to create labels for our data set. So we can create a labeling job, tell them where the data is sitting in our storage and ask them, involve humans from as a contractors, a workforce called Mechanical Turk with over 500,000 independent contractors, or use your own internal private workforce, your employees, to do this labeling, image classification, semantic segmentation, label verification. So humans in the loop. And that's what this Amazon SageMaker ground truth is about. Humans can annotate. We can do automatic annotations as well and then send it to humans to verify it. Okay, so ML life cycle can be broken into two main distinct parts. The first is the training phase. We've done the training, it's ready. The next part is to actually deploy the model so that it can start making those predictions on the unseen data. For example, that fraud detection model, we have our application which is sending a transaction to the Amazon SageMaker endpoint where our model is deployed. And it's saying, is this a fraud? No, it's not. Is this a fraud? Yes, it is. This process is called inferencing. I want to know if this transaction is fraud or not. And on AWS, Amazon SageMaker is the recommended service for deploying, also called hosting your model. We have model artifacts kept in the simple storage service. We also have CloudWatch monitoring that endpoint. And we're doing inferencing. Let's learn a bit more about what is this inferencing. So Amazon SageMaker inference, when you create an endpoint configuration, you must choose an inference option. So the first one is real-time inference. With real-time inferencing, your application or website send data to the machine learning model in few seconds and it quickly provides the predictions back. So this is like live prediction. I want to know right now if this email is spam or not. I don't want to wait for 1 week to know. I want to know right now if this transaction is fraud or not without waiting for a week. So here we have this real-time endpoint, which is live always, and it provides answers with low latency, low light, very quick, and it has a consistent performance. So great for applications that need fast responses like chatbots, recommendation engines. So here we have the model deployed on a persistent endpoint. We can also do batch transform. So in this case, the computer takes a large amount of data such as images or text, analyze it all at once to provide a set of results. So this is known as, this can be used for offline inferences. I have got 10,000 images and I want the model to classify them and then give me the result. It's not time sensitive. And it can take 24 hours or more to provide me the answer. I'm fine with that. So here, cost optimization is my priority. And batch transform provides 50% discount compared to on-demand pricing, compared to the real-time inference. Or I might have a situation where I want to do asynchronous inference. Asynchronous inference is near real time. So that means I'm happy to wait for like an hour or so if I have got a long processing workload, which do not have sub-second latency requirement. I can go for asynchronous inference endpoint. So long processing means I'm happy if it takes 20 minutes, 30 minutes, as long as it has a processing time up to 1 hour. And with this, I can give it a larger payload as well. So I have a loan application which is about 20 pages. I'm happy for it to go through those 20 pages, take its time, and come back with a response. Unlike that real time, that fraud detection, where my transaction is very small, 1 or 2 KB, and I want a response straight away in real time. Then we also have serverless inference. AWS provide this serverless inference to deploy models without configuring or managing any of the underlying infrastructure. So AWS will manage the infrastructure. This is ideal for workloads which have idle periods between traffic. So what happens here is I don't have any endpoint at all. In AWS, I cannot see any servers or anything. And suddenly my application has started asking questions, sending transactions for it to check. AWS will set up this endpoint. So there could be a little bit delay, a few seconds. So I'm not going to use it for fraud detection, of course. And this serverless endpoint will start working. So now I can send one app, or while it's doing, I can send thousands of transactions or ask it to predict these things. So it is going to scale out for me. AWS is going to make sure the endpoint scales out. All these are handled correctly. So we just upload our model. SageMaker will automatically scale up or down the resources as well, the resources which are needed to handle your inferencing workloads. So good for workloads that have idle periods between traffic spurts that can tolerate cold starts as well. People were creating their models for a long time. Every bank will have their own fraud detection models. Every company will start creating their own recommendation engine or models. AWS provides AWS managed AI ML enterprise grade solutions for all those common things, powerful capabilities designed to help organizations unlock insights at scale without creating their own models. So the services like Amazon Textract, it can extract text from documents and form. We have Amazon Recognition, which can analyze image videos to detect celebrities or sports stars. But without creating their own models, companies can start using these directly. Amazon Poly and many more. Kind of already built models for you. Now, if you want to go and have a look at these Amazon machine learning services, you can in AWS documentation. We have these machine learning and artificial intelligence AI ML services listed with their use cases and what they are good at, why people should use it. And if I want to go to check out Amazon Personalize, it'll give me information about ML service that makes it easy for developers to create individualized recommendations for customers using their applications. So no need to create a model to do that. We have this managed service already ready. Okay, so that's where we are going to end this session. See you in the next one. Bye-bye.